Okay, so what does the planner choose? He chooses a reward structure that hopefully implements the optimal cost threshold. So I'm thinking about this in two parts. What the planner would like to implement is some cost threshold that uses the options created by the ideas sensibly. That's embodied in his target cost threshold. But then the question will be, can he implement the cost threshold given that he doesn't observe who receives ideas and doesn't observe when they arrive? It's not like all the ideas are arriving in the planner's pocket. And that, of course, is the decentralized problem of innovation. If, in fact, everything were observable, as in the standard model of R&D, if the opportunities to put money into a production function were available to everybody, including the planner, there's clearly, for example, a much better set of incentives than intellectual property. I mean, if the planner knows everything, he can just choose the optimal plan and invest. The only reason you need decentralized schemes like intellectual property is precisely that the process is decentralized. So these ideas are arriving to people that the planner can't identify, and he doesn't know what the ideas are. If he did, he could just implement his optimal cost threshold directly. The only reason he needs an implementation scheme is precisely that these ideas are not common knowledge. And that really is the transformation of this subject that I'm looking for, that seems to me necessary to try to understand many things in the policy world, which I will return to at the end. Okay, so the plan of the paper is first to try to understand what is the optimal policy that the planner would like to implement, the cost threshold policy, and then to ask the question, is there a reward structure that will implement it? Can he choose a reward structure that will implement it? So here more specifically is the planner. So a viable idea, so if the function C is a cost threshold in time, telling you for each time what is the maximum cost that the planner would like to tolerate, if that C function is the policy, then what I call a viable idea at time t is an idea that satisfies the cost threshold. And viable ideas are arriving to the population at a rate lambda, but viable ideas are arriving to the population at a rate lambda times the probability that the cost threshold is met. So the viable ideas are arriving at a lesser rate. So the probability of arriving at time t without having had a viable idea, when the arrival rate is lambda, is this object. Now this looks very familiar from Poisson processes. This is the version of a Poisson process when the process is not stationary in time. And so instead of it being small lambda times t, which is the familiar probability of arriving at t with no idea, instead of that, you substitute basically the average hit rate. Okay, so t times t times the average hit rate is this object. Okay, so the planner, in order to choose the optimal cost threshold, remember what the planner is doing is trading off delay versus cost. And he has to know what he's trading off. So the delay, of course, is linked to his belief on the lambda. He doesn't know. The only thing the planner knows is that we have now arrived 100 years later. This market niche has not been filled. That's all he knows. Now, he also knows, up until that point, he knows what the implementation policy was. And if he was implementing the optimal cost threshold, he knows what the arrival rate would be on each lambda, and he knows what his posterior belief is on the lambda. This is what he knows, period. That's all he knows. So he has to have beliefs on the lambda. He has to be updating in time on the arrival rate of these ideas for how to fill the market niche. So he starts with some prior, which we'll call h tilde, and he arrives at time t hat. So his belief is, this is a probability density, his belief on lambda at time t hat depends on C. It depends on the cost threshold that has been implemented up until time t hat. And why is that? It's because he knows that many ideas have arrived out there, but the way he interprets the fact that no idea has filled the market niche, the way he interprets that has to account for the fact that some ideas were not used. And that's embodied in the cost threshold C. So the updating has to be with respect to the prior and with respect to the cost threshold C. And so he can calculate, there's no reason to follow this, but he can calculate the posterior probability of, calculated at time t, the posterior probability of arriving at time t hat, which of course is an average using his posterior beliefs on lambda. So now, of course, because this is a planning problem, it's a dynamic optimization problem, he's going to solve this by finding a value function. And what the value function is the value of continuing from time t when the cost threshold function is c, when he started with the prior beliefs h tilde. Okay, so the value function is, well, this is just the discounting from t. But if there were investment at time t hat, then the expected cost, this is notation for the expected cost of the investment at time t hat. The investment only takes place at time t hat if the cost is less than c of t hat. So this is the expected cost, conditional on the cost less than ct hat. So the value, if there's investment at time t hat, the value of that investment is the value of filling the market niche, which is the per period value V over R, minus the expected cost. And then, of course, the tricky part in writing the value function is you have to weight by the probability that the market niche is in fact filled at t hat. So there you're taking account of the posterior beliefs on lambda and so on. But think of this as the instantaneous probability, expected probability of filling the market niche at time t hat. This is the probability of arriving to t hat having begun at t. So now that's the value function. What does he do to optimize this value function? Well, he's choosing this C function. And why is this C function in the value, this C threshold function, why is it in the value function? It serves two different roles. It serves one role up to the t. It serves another role after the t. The C function up to the t is an ingredient to the planner's posterior beliefs at time t, because it's the cost threshold function that tells him how to interpret the fact that we arrived to t with no viable idea through this hit rate. At time t, he's choosing the cost threshold function from t going forward to optimize the value function. So that's the sense in which this C function plays two different roles before the t and after. Before it enters the updating on beliefs about lambda, after it's the choice variable. Okay, so he's optimizing at every t. He's optimizing this value function. This is the optimized value of going forward. That's what the value function is. Okay, so what will he do with this value function? So what do we know? So this problem, as all dynamic optimization problems, this problem will be solved by using the principle of optimality, which means that he optimizes going forward from every time t, but by the principle of optimality, the optimal path starting at any time t is the same. He does not, in fact, have to re-optimize. That is the principle of optimality. So he only has to optimize once. If he actually finds himself at t2, if there is no investment before t2, then he will find that, gee, the optimized C going forward from t2 that he anticipated at t1 is the same C that he would choose at t2. Okay. So here's the optimum. Here's the first order condition. What does this first order condition say? It says the planner will choose a cost threshold that has the feature that the value of investing now for the marginal idea, which means the highest cost idea that he would accept, the marginal idea, the value of investing now in the marginal idea is equal to the value going forward of weighting. Okay, so that's standard.